Hi, yes, Mike, we can hear you.
Okay, great.
Hi, everyone. We'll get started. So welcome everyone to this new Q&A session that we'll be offering regularly in the future. So my name is Julie. I am the coordinator for Discovered Universe. And today we'll have Mike Reed from the Dunlap Institute to answer your questions. The questions that you have live with us right now or that you've sent us in the last few days. So before I let Mike take over, I just want to mention how you can ask your questions. So of course you can join us live once a month roughly. So the next one will be on November 16th at 12 p.m. Eastern. So we're trying different times as well so we can reach different people all across the country and maybe even abroad. Um, so if you can't join us live to ask your question, and in fact, even if you can, it might be useful for us to know your questions in advance. This way we can find some visual support or find the answers if we don't know ourselves. So maybe if you think about it, just send them to us in advance. So you can send them to me directly with this email address, info@discovereduniverse.ca. If you are using Twitter, you can use the hashtag AskDU for Discovered Universe, AskDUAstro. And you can also, on our Facebook page, either write a message or a comment whenever we post something about this Q&A session. So there are different ways for you to reach us, and we'll be happy to take a few minutes once a month to answer them live. So for those of you who are online, feel free to type your questions in the chat box. And for those of you who are watching the recording, then maybe for next time, send them to us in advance, and we'll be able to include them in our presentation. So that being said, I will.
Okay, thanks, Julie. So hello, everybody. As Julie said, my name is Mike Reed, and I'm a professor of astronomy at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. And I'm going to be with you for however long you want to ask me questions about whatever you may want to ask about in astronomy. We have a few questions that were sent in by email, and I'll start with those. But any question you may want to ask about essentially any topic in astronomy, you're more than welcome to chat it in the chat box there, and I'll be happy to try and answer it. Hopefully, I can answer most of your questions, and if not, then I'll try and follow up with you afterwards. So, to give you some background, my expertise is in teaching astronomy to non-science experts, which is really appropriate given the questions that we received by email. And I think those were probably from Ed, who is with us now. The email came from someone called Ed. I'm going to guess it's the same Ed. Um, so I'm going to start with a couple of questions that Ed asked. And what I'm going to try and do is give fairly short answers to questions so that you can ask me the particular follow-up questions that you may have. And we won't waste all the time with me giving long-winded answers that way. Okay, so Ed asked three questions. And I'll start with his first one. So his first question was about how to explain what a black hole is to young people, to children, basically. And this is quite tricky. In fact, explaining what a black hole is to anyone is, in principle, quite tricky. What I suggest you do is, depending on the age of the child you're talking to or the expertise of the person that you're talking to, is you want to start them off with a bit of an understanding of what gravity is. So in my experience of explaining black holes over many years to students at the University of Toronto, they have a sense that anything to do with black holes or space or gravity is somehow a very distinct phenomenon from anything that happens on Earth. They think that special physics applies in space that doesn't apply on Earth. So I like to sort of ground them, literally in this case, ground them with an understanding of what gravity means to us locally. So if I was talking to a kid and I wanted to explain what a black hole was, I would ask them first, do they know what holds us to the Earth? What is it that prevents us from flying off into space? Why do we stick to the surface? And talk a little bit about gravity. You know, drop an object and say, why did that object fall? Why doesn't it just hover, for example? And once you have a sense that they understand something about gravity, I would move to the sort of next level of this question, which for me would be something along the lines of understanding if they know how gravity changes, what it depends on. So As you probably know, Ed, a black hole is essentially any highly compressed object. But to somebody who doesn't understand gravity well, that sense of the increase of the force of gravity with compression is not really obvious. People don't tend to have a sense of what creates gravity. They don't know, for example, that it depends on mass and distance from that mass. So instead, what I try and do is give people simpler, more intuitive analogies. Like if you were to compress the Earth, you squish it a bit, is that going to make it easier or harder for something like a rocket to blast away from the surface? And you may find that some people get a bit confused here, thinking that the smaller the Earth gets, the less of it there is, and therefore the easier it is to get away. So they might think about, for example, an asteroid, and they may know that it's easier to blast off from an asteroid than from the Earth. So you have to sort of emphasize that you're not peeling away parts of the Earth, you're not removing mass, you're compressing what's already there. And then you just allow that process to run to infinity, essentially, right? What if you kept compressing? Every time you compress the Earth more, it gets harder and harder for you to escape from it because you've got more mass, or well, you've got the same amount of mass, but compressed into a smaller volume. So you're closer to the center of the mass. You feel more gravity. And as you let that process run to completion, you would get a black hole, right? And this would be true no matter what you were compressing, whether it's the Earth, the moon, a star, anything. If you can compress it enough, you eventually compress it to the point where the fastest thing in the universe, which is light, can't escape from it. And that's the salient points I think about what a black hole is for a child. If you want to get into much more sophisticated aspects of black holes, things about time dilation or space-time curvature, aspects like that, that's a bit more complicated. I think it's hard to get into those things if you don't fundamentally have a sense that a black hole is just a thing with a very high escape speed. So you can try with that, and if you have a follow-up question, feel free to ask. I'll move on to your other two questions, and then we can come back as needed. People can ask other things. So Ed's second question was about describing the Big Bang. Now, this is I just said with describing black holes, I wouldn't necessarily go into space-time curvature or things like that. I wouldn't, for a first introduction to a black hole, I probably wouldn't start with your typical rubber sheet model where you put a dimple in a rubber sheet. People find that very confusing. Even undergraduate students with some science background usually get badly confused by those examples. That said, when it comes to something like the Big Bang, actually that is the kind of analogy I would use because it's, in my opinion, it's better than most of the alternatives. So you may be aware that we had a webinar a couple of weeks ago about the Big Bang and about answering difficult questions about it. And you can find the link for that online if you want to watch and learn a little bit more about how I explain the Big Bang. But the big problem a lot of people have with the Big Bang is to do with imagining that the entire universe starts off as a single point and that that point somehow exists in a void and expands to fill this void. It leaves people with lots of misconceptions. So what I do instead when I'm trying to explain the Big Bang, instead of starting from some weird initial condition of this everything in the universe compressed into a point that for some mysterious reason blows up into some mysterious space that pre-exists for reasons nobody understands, that's confusing. Instead, I think you can go the other direction. You can start with space the way it is today, and you can say space is filled with galaxies, and then huge amounts of empty space between those galaxies, and every day it gets a bit bigger. The space between the galaxies stretches, okay? But that means if you reverse that process, yesterday the space between the galaxies was smaller. And if you keep rewinding that process, it gets smaller and smaller and smaller and smaller until eventually all the stuff in the universe is packed together. So I just kind of drew a little graphic that I'll show you that tries to describe some of how that works. So again, here what I'm doing is I'm avoiding things like singularities, which are especially difficult. What does singularity mean to a child, right, or even to an adult? And definitely words like explosion, which are a bit iffy in terms of the misconceptions they may create for people. And then I emphasize words like expansion of space-time. So I just, for the sake of a visualization here, I drew a grid, and I drew dotted lines representing the fabric of space-time at some point in the history of the universe. And I drew the grid extending beyond the edge of the slide here. And the intent there is to emphasize the vast scale of the universe. You can imagine that the universe is infinitely big. And then I just picked some set of the grid cells in this set, and I highlighted them as a part of it that you could imagine is some chunk of the universe we're concerned with. Maybe the part of the universe we can see, something like that. And which wouldn't, of course, be a square, but for the sake of a grid, I'll draw it as a square. So you imagine some part of the universe that you want to concern yourself with, some sample chunk, and then over time, what happens to that chunk and to the universe as a whole is that it stretches. Okay, so any part of the universe you choose to begin with, any sufficiently large chunk of the universe that you choose to begin with, starts off small and compressed, and then it gets bigger and stretches as the whole universe stretches. And again, whether you start calling this image the present and saying this is the past, this is the further past, and then you get farther and farther into the past until the grid squares have all shrunk to effectively zero size, that's fine. That's a good way of explaining the Big Bang, looking back through time. Or you can start calling this the present and saying this is the future. It gets bigger and bigger as time goes on. Doesn't much matter. But the idea there is that you get rid of this notion that the universe was all compressed into a single dot that was floating in a void, which is an incorrect way of understanding what the Big Bang actually was. Now, this grid analogy may or may not work well depending on the person you're talking to. It has the obvious problem that it's a two-dimensional analogy instead of a three-dimensional one for the whole universe, but you can invite people to imagine it as a three-dimensional grid that stretches. So I don't know if that helps a little bit in describing what the Big Bang was. There are obviously many dozens of questions people will have. How big is the grid? How does the grid expand? Why did this happen? How do we know that this is happening? Those are all difficult questions. Many of them are answered in, as best we can, in that recording that you can find on the DU YouTube channel, I believe, or Julie can give you the link to it, and that may help. But if not, feel free to ask a follow-up question. Okay, so Ed's last question is perhaps the trickiest of them all, and that was, if you could travel at the speed of light, what would happen to time? So something that we often hear is that, maybe, at least I often hear, maybe you guys often hear this, is that there's no time for light because light travels at the speed of light, and at the speed of light, time stops. So that's a hard thing to explain, and there are a number of reasons for that. But I think a simple way of thinking about this question is to not think about light, but to think about matter, things like us, and ask not what happens at the speed of light, but what happens as you approach the speed of light, okay? So right now, if you have a watch on, a nice old analog watch, and you look at the way the hands are spinning, and you see that every second that passes, every second of time that passes, your watch dial advances 1 second. Your second hand moves 1 second forward. This will never change, right? You can go anywhere in the universe you want. You can move however you like. This will never change as long as your watch continues to function normally. However, it will change from somebody else's perspective. Someone else watching you will see that the rate at which time passes on your watch differs to the rate at which time passes on their watch. And the extent, the magnitude of the difference is a function of how fast you're moving relative to them. So this graph that I've popped up here shows you on the x-axis the speed that you are moving at as a fraction of the speed of light relative to somebody else. And on the y-axis, it shows you the factor by which your time is altered, is stretched relative to their time from their perspective. So to give a concrete example, what this graph tells you is that as I watch somebody in a spaceship whizzing away from Earth, if they are moving at 20% of the speed of light, so zero point 0.2 on the x-axis, then their time dilation factor, the factor by which their time is changing relative to mine, is almost 1. So it's basically the same rate of flow of time as mine. 1 second on my watch is almost 1 second on their watch. But if they go really quickly, if I look at them moving at zero point 0.9 of the speed of light, 90% of the speed of light, then the rate of flow of their time is around twice slower than my time from my perspective. So that means every time 1 second ticks on my watch, if I look at them, it will have only been half a second. Their time is going twice as slow as my time. And that effect, as you can see in the graph, gets more and more extreme the closer you get to the speed of light. So the faster somebody moves relative to me, the slower I see their time moving. Okay, the more their time is dilated, we say, relative to mine. But what's interesting about this graph, to get to your question, is you notice that as you approach the speed of light, so as you approach c, the speed of light, 100% on this graph, or 1, the time dilation factor shoots to infinity. And so what that means is that as someone flies away from me at the speed of light, the faster, or rather, as they approach the speed of light, so they're 99% of the speed of light, now they're 99.9, 99.99, the faster they go, the more their time seems to slow down from my perspective. But the thing about this is that for any material object, anything made of matter, like a person or a rocket, it's not actually possible to ever achieve the speed of light. This graph doesn't reach infinity when you reach the speed of light. It asymptotes, we say. It approaches the speed of light forever without ever actually, approaches infinite time dilation as you approach the speed of light without ever actually reaching the speed of light or reaching infinite time dilation. So in a practical sense, you can't actually do the thing that you were talking about, which is achieve the speed of light and have your time stop relative to somebody else's time. That can't actually happen. If you ask the question the way you originally asked it about, what does a photon see? What does light see? How does it experience time? It's a slightly iffy question. I think it's reasonably okay to say from a mathematical standpoint that, from the perspective of a light ray, there is no time. It's traveling at the speed of light, and the time intervals that it measures are, I suppose, if you like, they're zero from somebody else's perspective. It's not passing through time at all. But that isn't a perspective that any being made of matter could ever access. You can't ever experience that yourself, of being infinitely time dilated relative to somebody else. You can only get arbitrarily close to that experience without ever actually reaching it. So again, just to give a practical example, if I were to fly to the center of our Milky Way galaxy, it's about 25,000 light years. If you were watching me on Earth, if I was going pretty close to the speed of light, then you would see that it would take me about 25,000 years to fly there from your perspective. But if I flew there and returned, always traveling very, very close to the speed of light, then by the time I got back, it would have been about 50,000 years on Earth. But for me, it could have been an arbitrarily small period of time. It could have been, a second would have passed in my time frame. And the faster I made the trip, the bigger that difference in the time frames would be. So I hope that helps with your 3 questions. If you want to ask follow-up questions, or if other people want to ask questions, feel free to post them in the chat, and I'll be happy to try and answer them. So I'll give you guys a minute or two to chat away if you have questions. So I see Julie has posted the link there to the recording of the Big Bang webinar, which you can access on Adobe Connect.
While people are typing, I just want to say thanks, Mike. Actually, I learned something new too, so I really liked your explanations.
Thank you. Okay, we've got lots of people typing, asking questions. Give them another minute. Okay, so Ed asks, does not achieving the speed of light have to do with mass becoming infinite and thus you need an infinite amount of energy? There is an effect like that, yes. So as you approach the speed of light, again, you would not experience your own anything changing. Your clock flows at the same rate. Your mass remains whatever your mass normally would be for you. And all the other factors, you may also know that there's an issue with your size. It's called length contraction. Your length remains the same from your own perspective. But from somebody else's perspective, that's not true. From somebody else's perspective, watching you move at a high fraction of the speed of light relative to them, they see uh, you being shortened in the direction of motion, your time being slowed, and your mass being increased. And again, all of these things, all of these effects scale towards infinity as you approach the speed of light. So your mass from their perspective, goes to infinity, your compression in the direction of motion becomes infinitely high, you become infinitely compressed, and your rate of time slows effectively, almost to zero. So yes, you do have to deal with this effect that the faster you go, the more mass you appear to acquire from other people's point of view, and then the more energy is required to make you accelerate any further. Okay, so Linda asks, how can I explain the term planetary nebula? So Linda, in my introductory astronomy class for non-science students, I have a list that I give them of really, really terrible vocabulary in astronomy that is incredibly confusing. And this is one of those terms, planetary nebula. So for those of you who don't know, a planetary nebula is the remnant of a star like the sun after it runs out of fuel. So when a star like the sun runs out of fuel, instead of it, falling in on itself and becoming a black hole, the way a lot of people have heard or imagine, it doesn't do that. It just burns out. And in the process of it burning out, it actually goes through a period where it burns very, very hot for a short period of time, and that pushes its outer layers off into space. So you wind up with these incredibly beautiful arrangements of gas left over from what used to be a sun-like star, and they're called planetary nebulae, despite the fact that they have nothing to do with planets. They're called planetary nebulae, it is said, because when they were originally observed through small optical telescopes, which didn't have the power to resolve them and see what they actually were, they were sort of fuzzy colored dots. And if you looked out at the night sky with your own eye, you know that that's what planets look like. Jupiter or Mars, they look like, slightly fuzzy colored dots. So planetary nebulae, being slightly fuzzy colored dots, acquired this planetary connection, but they have nothing to do with planets. So usually what I do with people when I want to explain what a planetary nebula is say more or less what I've just said to you. I explain how they are created and why they got this inappropriate name, and then I encourage them to just acknowledge the name, but try and mentally dissociate it with the fact of what it actually is. Yeah. Hopefully that helps. Okay, so Ed says, kids ask me if it's possible that the Earth is inside a black hole. As well, they ask if we could be sucked into a black hole such as the one in our galaxy. If one could imagine a person alone in space nearing a black hole, what might occur? Okay, so could we be in a black hole? No, not really. There's a big issue with black holes that is not so obvious on Earth, although it's still present on Earth, which is something called tidal gravity. So if you imagine, Newton's law of gravity, it tells you that the force of gravity between two objects depends on the masses of those objects, but also the distance between them. And if you think about the implications of that, if you're standing upright on Earth, your feet are slightly closer to the center of the planet than your head. And that means that your feet are experiencing a slightly higher force of gravity from the Earth than your head is. And that difference in the force of gravity between your head and your feet is very, very small on Earth. But it's there, and you could measure it. We call it tidal gravity. It's the same sort of effect that produces the tides on Earth, which is where it gets its name from. In that case, it's the difference in the force of gravity on opposite sides of the Earth caused by the moon. But in the context of a black hole, tidal gravity becomes a really big issue. A black hole is a highly, highly massive, highly, highly compressed object. And that means that if you were to come close to a black hole, the difference in the force of gravity between your feet, if they were close to the black hole, and your head, if it's farther from the black hole, becomes extreme. So your feet feel a vastly stronger force of gravity than your head does. And this has, as you can imagine, very negative consequences. It leads to something that is fancifully named spaghettification, where you get stretched in the vertical direction, the direction pointing into the black hole. And if you go through the math, you see you actually also get compressed in the other direction. So you become sort of stretched into a piece of spaghetti. And if anything the size of a planet were to approach a black hole of any size, the tidal gravity would destroy the planet easily. So you can easily find evidence of this kind of thing from the collision of comet Shoemaker-Levy 9 with Jupiter in the mid-90s. When that comet approached Jupiter, again, the same sort of phenomenon happened. The intense gravity of the planet Jupiter spread out across the body of that comet. The comet felt more gravity on one side than on the other, and the difference in the two forces of gravity there tore the comet into many pieces. Same thing would happen to a planet like Earth if it approached a black hole. It would be shredded. In fact, we see evidence of this happening all the time. We don't literally see it, but if you look at a big black hole for long enough, with in particular an X-ray telescope, you see these flashes in X-rays from telescopes or from black holes like the one at the center of our galaxy. And what's causing those flashes is objects falling towards the black hole and being shredded violently, and they emit a big burst of energy. So no, we couldn't fall into a black hole, not under any realistic circumstances. You can imagine, there's a funny thing about black holes, which is that the bigger they get, the lower the force of gravity, or rather the lower the tidal gravity at their surface. So if you make a truly spectacularly huge black hole, then technically it would be possible to pass something through its outer boundary without the tidal gravity ripping the thing apart. But if you go through the calculations, first of all, that has to be a stupendously massive black hole, more massive than any that actually exists. And it wouldn't much matter anyways, because you'd be passing in at a very high speed, and it wouldn't be, you wouldn't be floating around for a long time inside a black hole. So that's more or less what would happen. Okay, so Voya says she teaches SES 4U, which is this high school Earth and Space Science class. And you say, I'd like to include a component on the history of astronomy. Do I have any suggestions as to interesting historical astronomers besides Galileo, Copernicus, and Tycho Brahe? That's a good question. So what I like to do in my introductory astronomy classes is I do talk about Galileo. And actually many years ago, I did the whole canonical set. I did Galileo, Copernicus, and Tycho. The whole canonical set of them. But after a few years of doing that, I got a little bit tired of it. I still retain Galileo because there's an interesting discussion to be had there about observing Jupiter's moons and developing the modern science of astronomy. And if you like, you can touch on his conflict with the church and things like that. But what I tend to do now is, particularly because I teach in Toronto, where it's a very diverse student body, is I try and pick astronomers that they've never heard of. And in particular, I try and pick, underrepresented astronomers, or astronomers, who are a bit off the beaten path. So for example, one thing I do when I'm teaching in March around International Women's Day is I pick up stories about famous female astronomers. And one of my favorites to talk about is Annie Jump Cannon, who was personally responsible for categorizing there are different estimates of the number, but multiple hundreds of thousands of stellar spectra, and giving us the system that we use for classifying stars. This was long before computers. Another really interesting one is Cecilia Payne, who was the person who first understood what the spectra of stars actually meant. She connected these, you take the spectrum of a star, you spread it out, and you see there's all these black lines in it. And she was the first one who figured out that all of those black lines were representative of the chemical composition of stars. And that was a huge leap forward in allowing us to understand the chemical composition of things beyond the Earth, which until that point wasn't possible. So that's what I do. Other people these days, another kind of fun thing you can do, depending on how much time you have and how much expertise, is look at the history of Islamic astronomy. So I like to point out to my students that if you look at the names of many of the brightest stars in the sky, most of them have names that are derived from Arabic names originally. And there's a whole history to Islamic astronomy that barely gets covered in most textbooks, but is incredibly important. So that's worth looking into as well. Yeah. So I see Ed typing another question. So while you type your questions, if you're interested in more female astronomers, a nice thing to look up is the Harvard Computers. These were a group of women who worked at Harvard College Observatory and made many of the foundational discoveries about modern astronomy. And they have quite interesting careers. Another one is Henrietta Swan Leavitt, who observed for the first time many of the the famous objects in the sky, things like the Horsehead Nebula and stuff like that, that a lot of people are familiar with. So I see Linda and Ed typing. Okay, Ed says, should we think of the Big Bang as a 3D event where from that one point everything went out to all points? If the Big Bang began from a single point, is that point now the center of the universe? Is there a center? No, so Ed, that's exactly why I don't show points. If you look in that Big Bang webinar that I gave right at the beginning or very close to the beginning, I show a slide of the typical way we represent the Big Bang, starting from a little dot and then expanding outwards from that. That is, as I say, it's a misrepresentation of the Big Bang, and it's a poor representation for exactly the reasons that your question highlights. For example, it implies that the entire universe began as a single point, which is very confusing. And it also implies that there's a center to the universe, which would logically be that point, and that there's an outside, which is not true. So we don't 100% for sure know the actual overall shape of the universe, but the data that we have are consistent with the universe being infinitely big. And if the universe is infinitely big, it doesn't have an edge. Things that are infinitely big don't have edges. And it also didn't start from a finite little dot, right? That doesn't make any sense to take a finite thing that somehow expands and becomes infinite. In fact, if you start off with an infinitely big universe now, and you use this expansion analogy in reverse, you say, great, it's infinitely big now, we'll shrink it by a factor of 2. It's still infinitely big, it's just more compressed, right? You can half the size of an infinitely big thing and it's still infinitely big, but you wind up compressing it more. And this is a better way of thinking about the Big Bang, that it started off perhaps infinitely big right at the beginning, however weird and unintuitive that may be. It starts off infinitely big, but also infinitely dense, okay, or effectively infinitely dense, incredibly dense. And then as it expands, the material spreads out as more space becomes available for it to spread out into. But it doesn't all start as a single dot, and it doesn't spread into a void. It can start off infinitely big and get bigger, so that things simply spread out without spreading away from a center, without spreading into a pre-existing void, without spreading beyond some initial edge. None of that has to be part of the model. Yeah, so Linda suggested spending some time talking about indigenous lore or ancient Chinese lore, Middle Eastern lore. I think that can be really great, depending on the age of your students and what their interests are and your expertise. There are a fair, there's not a ton of really great resources I find about those topics out there, but there are some. You can find some books on the sky lore of other cultures, and if your students are at the right age to appreciate sky lore and all the great stories and things like that, I think that's a fantastic thing to talk about. You can tell them about how, modern science picks 88 constellations to cover the sky, but that's sort of a choice of convenience. There don't have to be 88 constellations. It's just a historical accident. And of course, many other cultures don't use those same constellations, and nobody is obligated to use those constellations. Kids can go make their own if they want. Do I think that humans will ever travel at interstellar speeds and visit exoplanets and other suns? I think hopefully yes. You never know, but there's no physical law that would prevent that. Obviously, with current technology, if you wanted to get to even the nearest exoplanet, which is about 4 light years away, with current technology, that would take hundreds of thousands or maybe millions of years, and would be very, very difficult. However, technology changes very quickly, right? So if we choose to move in the direction of developing the technologies necessary to accomplish these things, there shouldn't be anything to stop us from doing that. It may take a while, I don't know that we'll ever achieve faster than light warp drives, who knows, but maybe we will. But even if we don't, even if we only ever use slower than light travel, I think it will be entirely possible to make it to other stars and visit other exoplanets and things like that.
One quick question, Mike. You mentioned I put links to the three female astronomers you talked about, but I only had two. Who was the other one again?
The other one that I mentioned was Cecilia Payne.
Okay, that's what I thought. Here it is. Okay.
Yep, there we go. There you got it.
Wasn't
Yep,
sure.
Cecilia Payne Gaposchkin. She's there's a great biography of her. I haven't read it, but my colleagues have raved about it, so you can have a look at that if you like. Ed says it's said that the Andromeda and the Milky Way will meet someday. Will there be giant collisions and possibly the destruction of one of the galaxies? Yes, on all counts. So Andromeda, you may know, is the nearest large galaxy to our own Milky Way galaxy. There are a couple of smaller galaxies that are closer, but in terms of other galaxies on the same scale as the Milky Way, it's nearest of those. And it is about 2.5 million light years away, which means that light from Andromeda takes 2.5 million years to get to us. And that may seem like a long time, and on a human lifespan it is, but on a cosmic scale, that's really nothing. That's the very closest big galaxy of billions of galaxies in the universe. And Andromeda is actually on a collision course with the Milky Way. They're two massive objects that are drawing each other closer together under the influence of their mutual gravity, and they will collide. And a nice thing I like to point out to students is we often talk about things that will sort of end it for humans, right? And well, eventually the sun will go out. The collision between Andromeda and the Milky Way will happen before the sun dies, before the sun runs out of fuel and becomes a planetary nebula. So in something like about 3 billion years, this collision will happen. And what will happen is these two giant galaxies, the Milky Way and Andromeda, come together, and they will pass through each other and go through a series of back and forth kind of swings before ultimately settling down and becoming a new merged galaxy. And that merged galaxy, you can say it will have destroyed both of the galaxies. It will have destroyed the Milky Way and Andromeda, but really what it will have done is rearranged all their parts. So currently, the Milky Way and Andromeda are both spiral galaxies. They're pancake-shaped galaxies. And when they merge, they will stop being pancake-shaped, and instead of winding up with something that's a plane, we'll wind up with a new galaxy that's a ball, a disk, or a sphere. And that's called an elliptical galaxy. That's actually, we believe, how elliptical galaxies generally form, and there are many elliptical galaxies in the universe. So those two galaxies will smash together. We'll get a new elliptical galaxy from the two of them, but individual stars and planets within each galaxy are unlikely to be strongly affected. The stars will likely continue to shine on as normal. They'll all be in new places, and maybe a few of them will collide with other stars, but in general, things will continue to proceed as normal. The sun will likely be chucked in some completely new direction and wind up in a brand new part of this new merged galaxy, but it will probably remain more or less the sun as we know it. He said it's estimated that there are more stars than grains of sand on the Earth. Is that probable or possible? Um, it is. It depends on where you're counting the stars. So there's a funny thing about the word universe. And that is that when we speak of the universe, we sometimes use that word in two different senses. One is the sense of everything that can exist, okay? All the matter, all the energy, all the stars, the gas, the dust, the dark matter, the dark energy, space, time, everything collectively, that's the universe. But a little bit more often, I think, when we say the word universe, at least among scientists, we tend to mean something subtly different, which is the observable part of that whole universe. And while the actual whole entire universe can be infinitely big and therefore can contain an infinite number of stars and planets, the part of the universe that we can see and ever will be able to see is constrained by the two factors. One, the fact that the universe isn't infinitely old, it began at some point, and the fact that the speed of light is finite. So um, it takes light time to move from place to place in the universe. So that means that in the 14 billion years that the universe has existed, not every place in the vast whole cosmos has had a chance to send light to us for us to see it by. So that means that there are huge, huge parts of the universe we simply can't see. And in fact, if you crank through the math, we will never see many of those parts. The universe is expanding too quickly for those parts to ever send light to us. And that means that, while in the whole universe you can have an infinite number of stars, obviously vastly more than the number of grains of sand on the Earth, within the observable part of the universe, the number of stars is finite, but still probably bigger than the number of grains of sand on Earth. It's still a very, very large number. There are, hundreds of billions of galaxies, each of which contains hundreds of billions or trillions of stars just within the observable part of the universe. So it's quite a large number. So I see Mike Jensen listening in there. Do you have any questions, Mike, that you may want to ask? Okay, great. Thanks. Ed says, do you think that we are wasting our time trying to get to Mars and there are other objects with more potential for life? So you may have been following in the news recently, Ed, that there have been a bunch of discoveries in the last few weeks about the presence of liquid water in various places around the solar system. A moon of Saturn, there's been talk about moons of Jupiter. The number of places where we're finding liquid water, which we believe is an essential precursor for any kind of life that we would recognize at the moment. The number of places where we find water like that is growing, even in just our own solar system. We know now that there is some kind of liquid water, at least periodically present on Mars. There's good evidence that liquid water flows at least occasionally on Mars. And there's permanent reservoirs of liquid water on several moons in the outer solar system. And that really raises our hopes that there might be life elsewhere. Do I think that we should aim for Mars first? Yeah, personally, actually, I do. Not all my colleagues agree. Some people think we should go to Europa first. Europa is a moon of Jupiter that has a large liquid ocean, because we know that there's a huge volume of liquid there, whereas on Mars, we don't know that there's a large standing body of water. However, Mars is relatively easy to get to, and there are lots of other reasons to want to go to Mars, human colonization and spreading through space, as well as looking for life that may be extinct on Mars, but still has left a fossil record. So I actually think Mars is a great place to go to, and I personally am, a big supporter of attempts to send people or even just robots, although I prefer people, to Mars. There is a mission, while you type your next question, there is a mission planned for Europa at some point in the not terribly distant future to send a probe to orbit Europa and learn more about the potential signs of life on that moon. Why have we not yet heard from any other intelligent life? You're thinking of the Fermi paradox. So for those of you who don't know the Fermi paradox, This is simply the idea that, when you think of space, it seems really big and vast, and, you think, oh, well, if we haven't seen any aliens, maybe it's just so big they haven't reached us yet. But that isn't really true. It is big and vast, but really quick kind of back of the envelope calculations suggest that it's not so big and so vast that we shouldn't have seen life yet. So the physicist Fermi, who kind of came up with this idea, phrased it more or less in the following way, which is our own Milky Way galaxy is about 100,000 light years across. 100,000 light years. That means light from one side takes 100,000 years to reach the other side. Long time, right? Seems like forever. But let's say you're some moderately advanced alien species. You're not Star Trek aliens. You don't have warp drives. You're not flying around at many times the speed of light. Let's say you can only go 10% of the speed of light. Now that's faster than we can go, but come on, 10% of the speed of light doesn't seem unreasonable eventually. Give us a few thousand years maybe. Maybe we'll be able to go faster than that. So imagine you can go 10% of the speed of light. To go from one side of the Milky Way to the other would take you 1,000,000 years at that speed. Okay, again, that seems really long, longer than humans have existed, basically. That seems too long. However, the Milky Way galaxy has been around for something like 10 billion years. So even if it takes 1,000,000 years to cross it, if you have 10 billion years to work with, you can make that trip 10,000 times in the lifetime of our galaxy. So if you imagine the Milky Way coming into existence, stars, 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 hundreds of billions of stars everywhere, a few planets around each star, a couple of those planets here and there form some life. Some of that life would probably have formed billions of years before we did, given how much time it had. And if any of those life forms were even remotely interested in exploring the galaxy, you tend to think that, it would only take them a few million years to cross the entire galaxy and kind of poke around into most of the corners. So if that's true, where are they, right? Why haven't we seen all these aliens zipping around the galaxy? Why aren't they talking to us? Why don't we find them moving around through the galaxy? And this idea is called Fermi's paradox, and there are a virtual infinity of solutions to it. Some of the more common ones are things like the zoo Earth hypothesis. The idea that maybe there are aliens everywhere, and maybe they are, not interfering with Earth. It's a sort of Star Trek Prime Directive kind of thing, right? Why aren't they talking to us? Well, you know, they're preserving Earth as an untouched civilization. There are loads more, ranging from optimistic to pessimistic. Maybe civilizations don't survive very long. Maybe everyone goes through a Cuban Missile Crisis and doesn't survive as nicely as we did. Maybe civilizations tend to wipe themselves out. Maybe most civilizations are so much more advanced than us that they're not terribly interested in talking to us, right? The example I often give to my students is, when was the last time you bent down and talked to a termite mound or an ant hill? I mean, you could, but why? You're not terribly interested in what their lives are all about. So you never know. Fermi's paradox is puzzling. It is puzzling to think, why hasn't anyone tried to make contact with us? Maybe life is very, very rare. Maybe most life forms aren't explorers the way we are and would rather stay home. Who knows? So it's a question on which we have too little information to try and answer it yet. Okay, Mike says, curious to know how to explain what a meteor is to grade 4 to 6 students. I use the analogy of rubbing your hands together to create friction, but I know that this analogy isn't quite accurate. Do you have a way to describe what's happening when a meteor becomes visible? Yeah, that's a good question. So I agree that the friction example is not quite right, but for a grade 4 to 6 student, it might be close enough. I mean, another analogy that you can use, which is a little bit divorced from astronomy, but still might help, is if you have a bicycle pump or anything where you're going to compress air. If you use a bicycle pump and you pump it really quickly, and you pump a lot of air into something, a bicycle tire or whatever, you can feel that the tire warms up because you're compressing air and you're compressing all the energy in that air along with the air. and that leads to heating. And you can perhaps use an analogy like that, that as a meteor flies through the atmosphere, it's compressing the air in front of it, which heats it up a lot. That's, yeah, off the top of my head, that's maybe the best analogy I can think of that might help students understand that. That said, I think also explaining it as to do with a kind of a friction, it's not quite accurate, but yeah, it's probably, Julie and I were talking about this the other day, about when you're explaining things to students, do you go with the thing that they can understand but is somewhat inaccurate, or do you go with the thing that may be above their level but is more accurate? Usually in undergraduate physics, we actually side with going with the slightly less accurate thing and then working our way up towards the accurate thing. So we, for example, we spend an entire year in first year physics teaching Newtonian physics, even though we know it doesn't fully describe the universe. And eventually they'll need quantum mechanics, but it's a bit hard to absorb quantum mechanics if you don't have Newtonian physics. So I would try the bicycle pump analogy, see if that helps. If it doesn't, yeah, maybe stick with the friction one for now. And you can for sure do an experiment. You can definitely pump things up and show that when you compress air or any gas, it gets hotter. Any other
Wow, that
questions?
was a very, very interesting Q&A session with lots of amazing questions for Mike. So thank you, Mike, for answering all of them so well.
You're very welcome. Yeah.
I'm just waiting to see if there are more questions, but maybe we can keep some for next time. If
Of course.
so, if you like this, actually, oh, sorry, Mike.
No, no, go ahead.
If you
Yeah.
like this session, feel free to spread the news. So this is like not even like no registration required, and we'll post the recording actually online as well, so people can, if you think about questions, and just say, "Hey, ask Discover the Universe," and they'll answer it. Um,
Yeah, and
awesome.
just I think it helps a little bit if you send your questions in beforehand. We can try and come up with appropriate visuals and other aids that may help explain things better. Yeah.
So I think we can end here for this time. So thanks again, Mike. That was amazing. And thanks everyone for watching, people who were there asking questions. I think Ed got a lot of great answers to his questions and other people too. So that was nice.
Great. Thanks, everybody.